Tahniah! Siaran langsung ini dibawakan khas kepada anda oleh Akademi YouTuber Malaysia, sebuah inisiatif e-didik Malaysia dan Kelab Guru Malaysia. Tumpukan perhatian anda, siaran langsung akan bermula sebentar lagi. Link sijil akan diberikan di hujung siaran ini. Pastikan diisi dalam tempoh yang ditetapkan. Terima kasih.
Hi. Good evening and hi teachers and all the wonderful students. Welcome to Pusat Tuition Academy YouTuber. Bermula percuma selamanya percuma. How are you doing today? I hope all of you are ready for today's lesson. Before we proceed, let's begin our session with prayers. Follow our on revisions. Okay, let me introduce myself to those who don't know me. I'm teacher Bibi Lau, the moderator of the day. So, I'm teaching in SMK Tinggi Ground, subject chemistry for around 19 years. Okay, then for the new timetable for chemistry lessons is on Sunday at 3:30 p.m. So it's for the Form 6 and matriculation students. So please set your reminder, put it in the timetable, okay? Let me introduce to the teachers on the stage today. So we have Teacher Tang as a presenter today. Hi, Teacher Tang. And we have Cikgu Shannon as a control host today. So Cikgu Shannon is teaching in College Matrikulasi Pulau Pinang. He has been teaching chemistry subjects for around 20 years. Then, so he's a control host for today. Then we have Teacher Kong Sweet Lee. She's teaching in College Matrikulasi Perak. Hi, Teacher Kong. So Teacher Kong has been teaching for chemistry subject for around 10 years. Okay. So let me introduce our presenter today. So our presenter today is Teacher Tang Yi-Yun. Okay, so she is teaching in College Matrikulasi Selangor. She has been teaching for around 8 years chemistry subject. So her topic for today is Hesss Law, Born-Haber Cycle. Okay. So before we begin, please support her channel by clicking subscribe button now. Okay. So for who haven't subscribed her channel, please subscribe to her channel. Make sure the button is gray color. Okay, and be sure to follow the class until the end. Okay. So before we begin, I have a few reminders to all of you. First, please pay attention to our lessons. Regarding the certificate link will be given at the end of our session. Please use e-didik account when you fill in your particulars. Okay, and the passcode will be given at the end of the session also. Please fill in the form within the time limit, which is 30 minutes. So without further ado, let's welcome Teacher Tang.
Selangor. So I've been teaching chemistry for 8 years. This is my poster. So I'm a member of pre-U chemistry group. So this pre-U chemistry group is led by Cikgu Shannon. So like what teacher Vivi Lau has mentioned before, So for the new timetable for chemistry live class, it is going to be on every Sunday, 3:30 p.m. Okay, so beside me and Jaegu Shannon, so for pre-U chemistry group, we also have teacher Lily Lau, Jaegu Mawar, and also Jackie Ron. Okay, so Jaegu Shannon is the control host for today's class, and teacher Lily Lau, the moderator, and the observer Jackie Ron for today's class. So beside chemistry, the pre-U also have the mathematics subject led by teacher E. So the members are teacher Eileen and Jegu Izana. And for the pre-U biology group, so it's led by Jegu Faiza. And the members are Jegu Fakia and also Jegu Naini. So for pre-U accounts, it's led by Madam Fizi and the member is Jegu Yati. So basically that's it for the pre-U group. So now we move on to today's topic. So today I'm going to go through Hess's Law, okay, focus on Born-Haber Cycle. So before I move on to Born-Haber Cycle, shall we recap first on a few definitions on the enthalpy change? So the first one is the standard enthalpy of formation. So still remember what is standard enthalpy of formation? It is basically the heat change when one mole of compound is formed from its elements in their simple state under standard conditions. So the standard state here is referring to the most stable state, the elements in their most stable state at room condition. So 25 degrees Celsius, 1 atm is the room condition. So must remember, according to the enthalpy of formation, the compound must be formed from the elements, and the elements must be in their most stable states at room condition. So for example, if given the standard enthalpy of formations for sodium chloride is negative 4010.9 kilojoule per mole, so how should we write the thermochemical equation? So based on the definition, one mole of compound. So and the compound here is sodium chloride. So when we write the thermochemical equation, we must write one mole of sodium chloride, and it is formed from its elements. So what are the elements forming the sodium chloride? It is the sodium and also the chlorine, and they must be in their most stable state. So for sodium, most stable state at room condition is sodium metal solid. While for chlorine, so from 4 you have learned halogen, they are diatomic molecules. Therefore, for chlorine, it will be Cl2 gas. Okay, and to write the thermochemical equation, you must write a balanced chemical equation. So to balance this, based on the definition, one mole of the sodium chloride compound. So means that here is 1 mole. So to balance this, the only way is to put half mole in front of chlorine gas. And in writing the thermochemical equation, you must also include the enthalpy change. And the enthalpy change here is the standard enthalpy of formations of sodium chloride. So you need to write the enthalpy change. If given the value, write the value and also the unit. So that is the enthalpy of formation. Must remember the compound is formed from the elements, and the elements must be in their most stable state. So that is enthalpy of formation. Then the second definition is standard enthalpy of atomization. So for enthalpy of atomization, it is defined as heat absorbed when 1 mole of gaseous atoms is formed again from the elements under standard condition, and enthalpy of atomization is always positive, always endothermic. So means that the value is always positive. Why? Okay, so shall we look at the example? So for sodium, the enthalpy of atomization's value is given positive 109 kilojoule per mole. When we write the thermochemical equation, so based on the definition, 1 mole of gaseous sodium atom being formed. Again, we must form from the element, and the element in the most stable state for sodium is sodium metal solid state. Okay, so can you see that in order to form this 1 mole of gaseous sodium atom, sodium solid need to absorb heat in order to sublime to become the gas. Okay, so solid change to gas. Therefore, heat need to be absorbed in order for the phase to change from solid to gas. Therefore, for matter, the enthalpy of atomization is always positive. And for thermochemical equation, do not just write the balanced chemical equation, must also include the enthalpy change on the right side. So how about for chlorine? So enthalpy of atomizations for chlorine gas is given as positive 121 kilojoule per mole. So how should we write the thermochemical equation? So again, definition, 1 mole of chlorine gas atom is formed from its element. So the element must be in the most stable state. So for chlorine, the element here will be the Cl2 gas. Remember, chlorine, halogen, group 17 element, diatomic molecule. Their most stable state must be diatomic molecule, and for chlorine is in the gaseous state. And then we need to balance the chemical equation. Based on the definitions of enthalpy of atomization, 1 mole of gaseous atom form, 1 mole of chlorine gas atom form. So in order to balance it, we only can put half mole in front of chlorine molecule, Cl2 gas. Okay, so this is thermochemical equation, so must include the enthalpy change as well on the right. So this is enthalpy of atomization. So again, enthalpy of atomization for molecule like chlorine is always endothermic, always positive. Why? For chlorine molecule, so it is chlorine molecule, in order to become atomized, become chlorine gas atom, you need to break the covalent bond. Therefore, heat need to be absorbed in order to break the covalent bond. Therefore, the enthalpy of atomization, be it for matter or non-matter, is always endothermic. Because for matter, sublimation, heat need to be absorbed for sublimations to occur, while for the non-matter like chlorine, heat need to be absorbed to break the covalent bond. Then now we move on to look at ionization energy. So what is ionization energy? First, ionization energy is defined as minimum energy required to remove 1 mole of electrons from 1 mole of gaseous atom to form 1 mole of positive 1 gaseous ions. Okay, so for example, we have magnesium. So how do we write the first ionization energy equation? So we have magnesium gaseous atom, 1 mole. According to first ionization energy, we need to remove 1 mole of electron. So remove 1 mole of electron, and the magnesium atom, after remove 1 mole of electron, it will become positive 1 magnesium ion. And the energy involved in removing this 1 mole of electron is what we call as first ionization energy for magnesium. And then, what is second ionization energy? It is the minimum energy required to remove 1 mole of electrons from 1 mole of positive 1 gaseous ion to form 1 mole of positive 2 gaseous ions. So after first ionization energy for magnesium, we get Mg plus 1 ion. Okay, Mg plus 1 ion. So for second ionization energy, we want to remove another mole of electron from this 1 mole of positive 1 Mg gaseous ion. So want to remove another mole of electron, and then now the magnesium becomes magnesium 2 plus ion. And the energy involved is what we call as second ionization energy of magnesium. So the fourth enthalpy change that I want to recap with you is electron affinity. So just now ionization energy remove electron. For electron affinity, it is opposite to ionization energy. For electron affinity, electrons is regained. Okay, so shall we look at first electron affinity first? So for first electron affinity, it is the heat release when 1 mole of electrons is gained by 1 mole of gaseous atom. After the 1 mole of gaseous atom gain the 1 mole of electrons, it will become 1 mole of -1 gaseous ion. So for example, we have oxygen gaseous atom. So gaseous atom. And then this oxygen gaseous atom receive or gain 1 mole of electron. So gain 1 mole of electrons. So after gain 1 mole of electrons, the oxygen become O minus 1 gaseous ion. And the energy involved here, the enthalpy change involved here is what we call as first electron affinity. Then what is second electron affinity? Second electron affinity is the heat absorbed when 1 mole of electrons is gained by 1 mole of -1 gaseous ion to form 1 mole of -2 gaseous ion. So after first electron affinity, the oxygen becomes O minus ion. So for second electron affinity, this O minus ion will receive another mole of electron, will gain another mole of electron and causes the O minus to become O2 minus ion. And the energy or enthalpy change involved is what we call as second electron affinity of oxygen. For second electron affinity, it is always endothermic, always having the positive value. Why? It is because after first electron affinity, we already get O minus ion. So this is negatively charged. And then, in order for second electron affinity to occur, this O minus ion, negatively charged ion, need to receive another mole of electron. Electron is also negatively charged. So, O minus negatively charged. Electron is also negatively charged. So, they will repel each other. Therefore, for second electron affinity, heat needs to be absorbed in order to bind the ion, negatively charged ion, and the electrons together. That's why the second electron affinity is always having the positive value. It's always endothermic. So the fifth enthalpy definition that we are going to look at is lattice energy. So what is lattice energy? So lattice energy is heat release when 1 mole of solid ionic compound is formed from its constituent gaseous ions. So for example, the solid ionic compound here is sodium chloride. So this is solid ionic compound. Okay, based on the lattice energy definition, it need to form from the constituent gaseous ion. So what are the ions present in sodium chloride? That would be sodium ion in the gaseous state and also chloride ion in the gaseous state. So when this cation in the gaseous state and the anion in the gaseous state come together, so heat is being released because ionic bond is being formed. Okay, and the enthalpy change involved here is what we call as lattice energy. So lattice energy, so basically will indicate the stability of an ionic compound. Okay, and for lattice energy, usually it cannot be determined experimentally. So I will do a video regarding on how we can look at the lattice energy magnitude to determine the stability of ionic compound. So if you don't want to miss it, so do subscribe my channel so that when I upload the video, you can have a look on the video. okay, and study more about how to use the lattice energy, okay, to determine the stability of an ionic compound. Okay, so I continue with enthalpy. So there are a few things regarding on enthalpy or enthalpy change that you need to know. First one is enthalpy is an extensive property. So what does it mean? So basically it means that the magnitude of the enthalpy change is proportional to the amount of reagent consumed and also the amount of product produced. For example, here 1 mole of methane react with 2 moles of oxygen gas to give you 1 mole of carbon dioxide gas and also 2 mole of water. And the enthalpy change involved is this much. When I double the amount of reagent and also the product form, can you see that the enthalpy change, the magnitude is also double. Okay, it's also double. Okay, so it is because, again, enthalpy is extensive property. So means that the magnitude is proportional to amount of reagents and product. When you double the amount of reagent and product, the enthalpy change will be double as well. If you multiply the reagent and product by 3 times, then the enthalpy change will be multiplied by 3 times as well. That is what meant by enthalpy change. Enthalpy is an extensive property where the magnitude of the enthalpy change is proportional to the amount of reagent and products. So second things you need to know about enthalpy or enthalpy change is when you reverse the reaction, the enthalpy change still having the magnitude equal to equal magnitude, but the sign will be opposite. Okay, so what does this mean? So like for example, the same reaction, 1 mole of methane react with 2 moles of oxygen gas to produce 1 mole of carbon dioxide and 2 moles of water. And this is the amount of enthalpy change involved in this reaction. So now we reverse the reaction. So what does it mean by reverse the reaction? It means that now the product become the reagent, okay, and the reagent become the product. So when you reverse the reaction, can you see that the enthalpy change still having the same magnitude, but the sign becomes opposite. Okay, so this is the second things you need to know regarding on enthalpy change. So now to test your understanding, so question number 1. So determine the heat of the reactions for the following reaction. So any students answer? So what is the heat of reaction for this reaction? Can you see that you have been given this reaction and this is the enthalpy change? And for this equation, it is half of the basically the amount of reagent and product have been half. So what will happen to the enthalpy change? It is expected to be half as well. Therefore, the answer is A. So now we move on to look at question number 2. So given, so this is the equation for the lattice energy, and this is the lattice energy value. So ask you to determine what is the lattice dissociation energy for barium fluoride. Can you see that for the lattice dissociation energy, the equation is being reversed. So when reverse the equation, what will happen to the enthalpy change? Any students want to answer?
So far, no yet.
Okay. So never mind. Then I will review the answer. So remember, just now I told you already for the enthalpy change when we reverse the reaction. So reverse the equation. The magnitude of the enthalpy change is still the same. Yeah. But the sign becomes opposite.
Student answer. Attila answer B.
Okay, B.
Amira.
Okay, good. Very good. Very good. So that is the correct answer. Okay. So when the equations reverse, the magnitude is still the same, but the sign become opposite. Very good. So now, okay, I can move on to the Hesss Law. So Hesss Law defines that when reactants are being converted to products, the enthalpy change is the same whether the reactions is taking place in one step or in series of steps. So what does it mean? So basically, it means that a reaction where reactant A is being converted to product C. When a reactant A is being converted to product C, so this reaction can take place in one step. So this is one step. Okay, so or it can also happen in series of steps passing through B. So whether, according to Hess's law, whether the reactions is happening in one step or in series of steps, the total enthalpy change is still the same. Okay, it's still the same. So because of that, we can equate the equation to give us delta H1. So this is the one-step reaction. The enthalpy change involved is delta H1. Okay, or it can, to convert A to C, it can also happen in series of steps, okay, and then when it happens in series of steps, so this is the total enthalpy change. According to Hess's law, doesn't matter happening in one step or in series of steps, the total enthalpy change is still the same. Therefore, you can equate the equation to give you this. Okay, so basically, what is the applications of Hess's law? Hess's law is used to determine the enthalpy change or heat of reactions, which cannot measure directly through experiment. Okay, so and and just now I mentioned for lattice energy, it cannot be determined experimentally because it is too difficult for us to separate the solid ionic compound into the respective gaseous ion. Therefore, it is very difficult to determine lattice energy experimentally. However, how can we determine lattice energy for each of the ionic compound? We can determine it by applying the Hess's law. This is what I'm going to teach you today. Okay, so now we can move on to look at Born-Haber cycle. So Born-Haber cycle basically apply Hess's law in ionic solid, And by applying Hess's law, we can determine the lattice energy for the solid ionic compound. Okay, so how can we do that? Okay, basically by combining a few processes, okay, a few enthalpy of several processes such as enthalpy of formation, enthalpy of atomization, first ionization energy, and also electron activity. Okay, so for example, how can we determine lattice energy for potassium fluoride? How can we determine the lattice energy for potassium fluoride? So this is, so in order to determine the lattice energy for potassium fluoride, so first thing we need to do is look at what is the ionic compound that is being given to us. Like in this question, we are being given potassium fluoride. Okay, so this is our ionic solid or ionic compound. Okay, so after we have identified our solid ionic compound, okay, then we can write the enthalpy of formation equation. So still remember how to write the enthalpy of formations equation. So we must remember for enthalpy of formation, this solid ionic compound is formed from its element. So what are the elements in potassium fluoride? So that will be potassium metal and also fluorine gas. Must remember for this is solid ionic compound, okay? So this solid ionic compound is formed from its element according to enthalpy of formation. It is formed from its element, and the element must be in the most stable state. So for potassium, most stable state is solid state, solid potassium matter. Okay, and for fluorine, it will be, so again, fluorine is halogen, group 17 element. It must be diatomic molecule. Okay, so their most stable state is diatomic molecule, and for fluorine, it is in the gaseous state. Okay, and then to balance this equation, so can you see that it is defined as 1 mole in enthalpy of formation? The compound is defined as 1 mole. So in order to balance the equation, the only way is to put half mole in front of fluorine gas. Okay, and the enthalpy change that involved is the enthalpy of formation. So you can write that in your equations first. Okay, and then can you see that this is potassium matter, and this is non-matter. So in Form 4, you have learned how to form solid ionic compound. So you form it from matter and non-matter, and according to the enthalpy of formation. So this matter and non-matter must be in their most stable state. Okay, so beside forming from the matter and non-matter, solid ionic compound can also form from the cation and also the anion. So from matter, how can we get the cation? And from non-matter, how can we get the anion? So after you write the enthalpy of formation, what you need to do is, you know that this is your solid ionic compound, so you identify what is your cation and also your anion involved. Okay, so must remember.
No, already past 30 minutes. We have a break now.
Oh, okay. So we stop a while for
Tuition
the
online percuma. Tuition online percuma. Layari www.academyyoutuber bagi mengikuti tuition online secara percuma. Prasekolah, sekolah rendah, sekolah menengah, semua ada di Akademi YouTuber. Rujuk jadual di laman sesawang www.academyyoutuber.com. Semoga masa terluang anak-anak anda diisi dengan sebaiknya. Tuition online percuma mestilah Akademi YouTuber.
Okay, Teacher Tang, you can continue.
Oh, okay. So I continue. So after written down the enthalpy of formation, so again in Form 4 you also learn, okay, in order to form solid ionic compound, not necessary from the element matter and non-matter, can also be formed from the cation and also the anion. Okay, and must remember matter will form the cation. So how can the matter form the cation? So in Form 4, you learn matter will donate electron. Okay, so means that electron need to remove from the matter atom in order to become the cation. And for non-matter, okay, non-matter atom will receive electron to become the anion. So with that concept in mind, then now we can continue to draw the Born-Haber cycle. So just now we already identified the potassium is the matter. Okay, so in order for it to become the cation, so first it need to be atomized first. It need to be atomized, become gaseous atom. It need to be atomized, become gaseous atom. So in order for it to atomize to become gaseous atom, so the enthalpy change that involved is what we call as enthalpy of atomizations of potassium, and given this is the value. Okay, And then after the metal has become the metal atom in the gaseous state, so this is the metal atom in the gaseous state, then the potassium metal, so it needs to become cation. So how can it become cation? This is atom in the gaseous state. How can it become the cation? By removing one more of electron. So after remove one more of electron, it becomes potassium ion. Okay, we get the cation that we want. And the energy involved to remove one more of electron from potassium atom to form potassium ion is what we call as first ionization energy of potassium. Okay, and then how about the non-metal fluorine? It needs to become the anion. It needs to become the anion. So again, this is molecule. Okay, so you have learned it needs to become atom first, then only it can receive the electron. So how can the molecule become atom? Again, involve atomization. So from the molecule, we need to atomize it, so break the covalent bond to become the fluorine atom. Okay, and the enthalpy change that involved is what we call as enthalpy of atomizations of fluorine. So after fluorine has become the fluorine gaseous atom, then it can receive the electron. It can receive one more of electron. So the receive one more of electron become fluoride ion. Okay, and the enthalpy change that involved is what we call as first electron affinity of fluorine. Okay, so now we already get the cation and also the anion. Then the cation and the anion, they can react with one another to give us the solid ionic compound. So when the cation in the gaseous state and the anion in the gaseous state come together, heat is released, and that heat release is what we call as lattice energy. Okay, so now how can we calculate the lattice energy? So can you see that based on the circle that I draw, so the enthalpy of formation, so this step is one step. And then the rest are the series of steps, because this is the reactant and this is the product. So the reaction can occur in one step where the element metal and non-metal react to give you solid ionic compound, or it can happen in a series of steps. Okay, so now is the Hesss Law coming in for us to write the equation. So one step is the enthalpy of formation is equal to the enthalpies of the series of steps, which involve enthalpy of atomization of potassium, first ionization energy of potassium, enthalpy of atomizations of fluorine, first electron affinity of fluorine, and also the lattice energy. Then what we need to do, we just need to put in the value that is given to us accordingly. Then we can calculate the lattice energy for potassium fluoride as negative 817.7 kilojoule per mole. So that is the first example. So now I show you the second example. So how to determine the lattice energy for potassium oxide. So again, okay, so just now I already told you we need to start with enthalpy of formation. Okay, so enthalpy of formation for the solid ionic compound potassium oxide. Okay, and then, okay, so shall we write the equations first? So our solid ionic compound here is potassium oxide. So potassium oxide. So remember, enthalpy of formation, this potassium oxide must form from its element. So what are the elements present in potassium oxide? So is potassium metal and also the oxygen gas. So the element must be in their most stable state. So potassium is the metal. So most stable state is solid metal. Okay, and for oxygen at room condition, most stable state is O2 gas. O2 gas. Okay, so, and then to balance the equation, can you see that to balance equation? So enthalpy of formation define 1 mole for the compound form, 1 mole for the compound form. Therefore, to balance the equation, we need to have 2 moles of potassium metal react with half moles of oxygen gas. And the enthalpy that involved is what we call as enthalpy of formation for potassium oxide. Okay, and then can you see that this is the metal and this is the non-metal. To form solid ionic compound, beside forming from the elements metal and non-metal elements, they can also be formed from their cation and the anion. Okay, so for potassium oxide, the cation here is potassium ion and the anion here is the oxide ion. Okay, so from the metal residue, how can we make it into cation potassium ion? So again, first we need to atomize it. We need to change it to gaseous atom first, then only we can remove the electron. Okay, so can you see that here from 2 moles of potassium solid to become 2 moles of potassium gaseous atom, the enthalpy change that involved is enthalpy of atomization. But then, remember, enthalpy of atomization defined for 1 mole of potassium atom form. Here, we are forming 2 moles of potassium atom in the gaseous state. Therefore, we need to multiply by 2. Remember, the enthalpy change, it is proportional to the amounts of reactants and product. So here 2 times, therefore the enthalpy change must multiply by 2 as well. So after we get the gaseous atom, okay, our goal is to get the cation. So how can we get the cation? Okay, so metal atom in the gaseous state, we need to remove 1 mole of electron. So after remove 1 mole of electrons, then we get the gaseous ion, positive 1. Okay, but to balance the equation, it must be 2 mole, 2 mole. Therefore, we need to multiply the first ionization energy by 2. Okay, because remember, first ionization energy, okay, is defined for 1 mole. 1 mole of electron being removed from 1 mole of potassium gaseous atom. But here we have 2 moles of potassium gaseous atom. Therefore, 2 mole of electrons is being removed. That's why we need to multiply by 2 for the first ionization energy for potassium. So we already get our cation. How about our anion, oxide ion? So how can we get the oxide ion? Also the same thing. First, we need to atomize the molecule. So we have O2 here. This is molecule. Molecule, we cannot straight away get the ion. Okay, we need to atomize it. We need to change it to atom first. So atomize it, so giving us oxygen atom. So the enthalpy change that involved is enthalpy of atomization of oxygen. Okay, so again, you see this is 1 mole of oxygen atom being produced. Okay, being formed. Therefore, it's just times 1 actually. Okay, so our goal is to get O2 minus, O2 minus. So after we get the oxygen atom, so the oxygen atom gain 1 mole of electron. So gain 1 mole of electron to become O minus ion. Okay, so the enthalpy involved here, enthalpy change involved here is first electron affinity, because gain 1 mole of electron, the oxygen gaseous atom gain 1 mole of electron. So gain 1 mole of electron, so that is first electron affinity. Then giving us O minus ion. And then O minus ion, need to gain another mole of electron because we want to form O2 minus ion. Okay, so need to gain another mole of electron. So to form O2 minus ion. Okay, and the enthalpy change that involved here is what we call as second electron affinity of oxygen. Then the cation and the anion can react to form the solid ionic compound. So the gaseous cation and the anion that react to form the solid ionic compound, so basically release heat, and the heat release is what we call as lattice energy. With this energy cycle, Born-Haber cycle energy cycle, we then can calculate the lattice energy for potassium oxide by applying the Hesss Law. Still remember, Hesss Law stated that when reactant being converted to product, whether the reaction is taking place in one step or in series of steps, the total enthalpy change that involved is the same. So our one step here involves enthalpy of formation. Okay, and the series of steps involve enthalpy of atomizations of potassium. First ionization, 2 times first ionization's energy of potassium. So enthalpy of atomizations of oxygen. First electron affinity of oxygen, second electron affinity of oxygen, and also the lattice energy. So you can write the equation based on the Hesss Law. And then to calculate the lattice energy, we just need to put in all the value. So we can get the lattice energy as negative 2331.4 kilojoule per mole. Okay, so I move on to give you another example. So sometimes, not necessarily the questions will ask you to find the lattice energy. So they might give you the lattice energy but ask you to calculate the enthalpy change of another thing. Again, like in this question, they ask you to determine the first electron affinity for chlorine. So how do we do this question? So it is still the same. First, you need to construct your Born-Haber cycle for the solid ionic compound. So again, for this question, the solid ionic compound that we have is barium chloride. So again, first step, after we have identified the solid ionic compound, we write the enthalpy of formation. So what are the elements, the metal element and the non-metal element forming the barium chloride? So the metal element here is the barium solid, and the non-metal element here is the chlorine gas. Okay? And the enthalpy change that involved is what we call as enthalpy of formation. So after we write our enthalpy of formations equation, okay, must remember this solid ionic compound can also be formed from the ion. So what are the ions in barium chloride? So that is barium ion and also chloride ion. So from the metal, how can we get the cation? So again, first we need to atomize the metal. Make it into gaseous atom. Then for metal, we need to form cation. So we need to remove the electron. So when remove electron, it involves ionization energy. Okay, so we need to remove one by one. So remove one more. So give us barium ion, positive 1. And the enthalpy change that involved is first ionization energy of barium. So our goal is to get barium 2+. So means that we need to remove another mole of electrons from the barium positive 1 ion in order to give us barium positive 2 ion. So, and the enthalpy change that involved is second ionization energy of barium. Okay, so we already get the cation, so it's good. Then how about the anion? So from the non-metal, So this is molecule. We need to change to atom first. So this involves atomization energy, enthalpy of atomizations of chlorine. Okay, so can you see that here 2 mole of chlorine gaseous atom is formed. Therefore, it means that it involves 2 times the enthalpy of atomizations of chlorine, because enthalpy of atomization of chlorine defined only for 1 mole of chlorine gaseous atom form. But now we are forming 2 moles, therefore need to multiply by 2. And our goal is to get chloride anion. So means that this chlorine atom need to receive 1 mole of electrons. So here 2 moles of chlorine gaseous atom receive 2 mole of electron to form 2 mole of chloride gaseous ion. Therefore, it is 2 times the first electron affinity of chlorine. Okay, and then after we get the cation and the anion, they can react to form the solid ionic compound. So that, and the energy release is what we call as lattice energy. Okay, and then we can apply Hess's law to write the equation. So what this is our reagent and this is the product. So this is the one-step reaction involve enthalpy of formation. Okay, and these are series of steps. So you can equate them. So enthalpy of formations, therefore, is equal to the sum of the enthalpy of atomizations of barium, first ionization energy and second ionization energy of barium, plus 2 times enthalpy of atomizations of chlorine, 2 times first electron affinity of chlorine, and also the lattice energy for barium chloride. So after equate them, you just need to substitute the value to find, the question asks us to find the first electron affinity for chlorine. So the rest is just mathematics. So you just need to substitute and then calculate what is your first electron affinity for chlorine. And for this question, it is determined to be negative 346 kilojoule per mole. So any questions so far? No questions from the students? Okay, so if no question, then move on to question number 3. So I already give you the BornHaber cycle for sodium oxide. So now, based on the information that are being given to you, can you calculate what is the enthalpy of formations for sodium oxide? Again, apply Hess's law to write the equations first. So, any question, any answer from the students?
So far, not yet.
Okay, not yet. Okay, so
They still calculating.
okay, they are still calculating. So write the equations first. So remember Hess's law, this is the reagent and this is the product and this is the one step. This is the one step. Therefore, the enthalpy of formation is equal to the, so the enthalpies for the series of steps. So 2 times the enthalpy of atomizations for sodium, and then 2 times the first ionization energy for sodium, plus the enthalpy of atomizations of oxygen, plus the first electron affinity of oxygen, plus the second electron affinity for oxygen, plus the lattice energy. Okay, and to calculate it, you just need to you just need to substitute the
Teacher Tang, there's
just
an
need
answer
to
from Azila. Negative 416.
negative 4.
Her height also, mouthpiece and her height also negative 416.
Okay, very good. So the answer is correct. Negative
Zafika also.
416 kilojoule per mole. Okay, very good, very good. So, so now the last question. Okay, so determine the lattice energy for magnesium fluoride. So how to do this question? So construct the Born-Haber cycle for magnesium fluoride first. Again, first write the enthalpy of formation, then the metal you atomize it, and then change it to cation by removing the electron. So the enthalpy change that involved is ionization energy. For the non-metal fluorine, again atomize first, and then after you atomize it, so you need to, for non-metal, so after you get the atom, you need to receive electron, gain electron in order to become the anion. And the cation we get with the anion, then give you the magnesium fluoride solid ionic compound, and the energy involved is the lattice energy. Any answer from students? Yeah, this one they need some time to do. Okay, so shall we have a look? So this is the Born-Haber cycle, energy cycle that you can construct. Okay, and to calculate the lattice energy, so first you need, after you construct the cycle, you just need to apply Hess's law. So one step and the series of steps. So one step involves the enthalpy of formation. So, and the series of steps involve the enthalpy of atomizations for magnesium, first and second ionization energy for magnesium. And for non-metal, you atomize first. So 2 mole of fluorine atom form, so you need to multiply by 2. And then this 2 mole of fluorine atom receive 2 mole of electron. Therefore, it's 2 times the first electron affinity for fluorine. Okay, and then you should get your lattice energy equal to negative 3,122 kilojoule per mole. So basically, that's it from me for today. So, any questions? So no question, then back to the moderator.
Okay, thank you, Teacher Tan.
Okay.
So we are done for today's session. I hope you learned a lot from Teacher Tang about Hesss Law and BornHaber Cycle. Congratulations to those who are able to follow our session from the beginning till the end. And thank you very much, Teacher Tang, for such an interesting lesson. Before that, students to check out the link for the certificate in the comment section, and the passport also in the comment section. Do remember to subscribe to Teacher Tang's channel for more videos, okay, from her. Remember, the link will only be active in 30 minutes, so please click and fill in the form with correct spelling. Okay. To those who haven't joined the EDD Junior Telegram, you can do so. You can find the link email for the application of EDD Junior at the description or the comment section. Okay. So once again, I would like to thank teacher Tang for the interesting lesson. I think that's all for now. We will see you in another session. Good night, everyone.
Berikutan pengumuman penutupan sekolah sehingga akhir persekolahan. Pengajaran dan pembelajaran secara home-based learning tetap diteruskan. Oleh itu, kami di Akademi YouTuber menyediakan tuition online percuma pertama di Malaysia dari prasekolah hinggalah ke sekolah menengah dengan kerjasama E-Didik Malaysia dan Kelab Guru Malaysia. Kenapa bayar jika anda boleh dapat percuma? Bermula percuma, selamanya akan percuma. Manfaatkan peluang yang ada. Jangan tunggu lagi, sertailah sekarang. Untuk maklumat lanjut, layari www.academyyoutuber.com.
Dibawakan kepada anda oleh Akademi YouTuber.